So welcome. Yeah, I also speak English because mijn Nederlands is heel slecht. I'm trying, but I'm horrible at it. I turn it on. Yes, I turn it on. I unmuted it. Good. So that's why I'll go to English. So I'll talk a bit about memory today and a little bit about sleep. And one most important thing, if you have a question, just raise your hand, make a noise, be noticeable. Just ask when it comes up, because we're going to pop through different topics, so it's always easiest if you just ask it when the question comes up. So we're going to first off, before we're going to go into the topic of sleep and memory, we're going to actually look at each topic in a way individually. But before that, let's quickly say what is sleep and memory. So sleep and memory is this phenomenon that we know already for a while, that both in the skills domain as well as in declarative knowledge, so about any kind of information you want to learn, you can practice, you can learn, you can encode, you can read, but you actually will reach a limit of performance. And only if you stop, take a nap, sleep a little bit, you'll suddenly be much better. And this is what we call the consolidation or memory consolidation that occurs during sleep. And one of this, especially in the skills domain, maybe some of you have already noticed this effect. So anybody who's learned an instrument, or in my case, I dance, so I do choreographies where I have to learn sequences of movements. Any of those, you probably have experienced this feeling that it doesn't work, it doesn't work, it doesn't work. But if you go away and you come back, suddenly the movements flow. And this is memory consolidation during sleep. That's why actually with most of my students, I like doing, there's a simple finger sequence task we use in human subjects. And that's one that's very nice to do with students because it's something where you can feel it in your own hand. You can feel that your performance went better over sleep. And how this is happening, that we don't know. And that is what we're trying to find out. But as I said, before we go into that, let's start very simple. This is a brain. Generally in the brain, we have lots of neurons. So neurons are these great cells that fire or that communicate with other cells with electricity. So in a way what they do, one cell will connect to another cell, create an electrical impulse which can be then translated via a chemical signal in the synapse to another electrical impulse in another brain. Now how these fire we can measure, of course, by putting an electrode to the brain. Most of the work I do actually is with rodents, and with rodents we have the freedom of at least even delving deep into brain areas, because for example this yellow brain area is the hippocampus, which I'm very much interested in. But in humans we usually stop actually on the surface. So we tend to not go into the brain. Usually. There is a special population of patients that have a chronic epilepsy who will anyways have electrodes in their brain to be able to pinpoint where the epilepsy occurs, and so that you can remove it. And those subjects are very popular in my field because we love getting our hands on them, because they're anyway sitting around for weeks in a hospital, so they can do some memory tests. But of course, I actually don't work with these patients. I would love to, but I don't. So that's why I stop at the surface. And then, of course, usually when you're in the wake state, what will happen is your neurons are going to fire totally differently. So every neuron will fire at a different point. You have smaller, in a way, groupings. And this desynchronized firing, what we can read out if we put this electrode on the surface, will be this small amplitude kind of signal. Now, one of the main changes that occurs when you go from wake to sleep is that your neurons are now going to fire way more synchronous. And so in a way, what this will result in our surface electrode is that we now see what we will call a slow oscillation. So that's why these are what we call oscillations. But a slow oscillation, and the main reason you could see it in a way of summation activity. So to summarize, let's see if we could do this, we could simulate this. But to get a feeling of how this occurs, we can actually not only use electrical signals, we can use sound waves. So what I would ask you now to please just start clapping. Everybody just clapping. Thank you, it worked. It doesn't always work, but it works really good. So as you may have noticed, we just summarized most of the phenomenon us oscillatory researchers like to watch. Number one, when you started, you were desynchronized, so that's why you were totally, it was a continuous noise level, as you may have noticed. But then I came as a pacemaker, very subtly, trying to pace you a bit, and then what happened is that you now were more synchronized with your firing, so with your clapping, and so if we would have now measured the sound level level in the room, you would have seen exactly a classic oscillation. So this is exactly how these signals occur. It's just with electricity. And you also have a pacemaker. So me in the brain is actually making you sleep in a way. So that me is the thalamus. So I will make you sleep. But that's exactly also how it works. And these pacemakers are often from the outside, so we don't know this all about oscillations. Some of these, in a way, are epiphenomena because the brain is firing and doing things. But sometimes, especially with the slow or the sleep oscillations, you have pacemakers in the brain. So third brain areas, in a way, that are enforcing oscillation onto other brain areas to synchronize them. Now, when we actually look into sleep, so with humans, this is kind of how it can look like if you want to do research. So we have electrodes that sit on the surface of the brain. Those are our electroencephalograms, so EEG, to measure the brain waves. Here's the minimum for sleep. You will have 2 on the central area. Currently, actually, nowadays, there are newer scoring systems where you need at least 6 electrodes. But of course, we at the Donders even have systems where you can record up to 128 electrodes across the brain if you really want to do a good spatial resolution. But one thing that's different in why we call sleep recordings polysomnography instead of EEG, as you would know it from wake research, is because we also add the electrooculogram, so EOG, to measure the eye movements, and we measure the EMG, the electromyogram, to have muscle tone. And especially the eye movements are actually quite funny, because I don't know if you were aware of it, that your eye is one big dipole. So it turns out your eye is perfectly polarized through the front of the sclera versus the back of your eye, where you actually, of course, see things. And so that means if you're moving your eye, you're actually creating a perfect electrical signal, which we can now capture because it's a dipole. And with the EMG, of course, it's just the tension that you can measure. And the reasons we need these different things is to be able to differentiate different sleep stages. And now the question, of course, have you ever heard of a sleep stage? What is a sleep stage you know? Just REM is a classic one. Everybody knows about REM. If there's non-REM, is there anything else than REM?
Slow wave sleep.
Slow wave sleep. Yes, that's the other one.
C4.
Ah, we have an expert. Yes, so in a way we now already have something. So how you usually would say it, so number one, REM always everybody says, but ironically REM is the smallest portion of our sleep. It's just like 20% of our sleep. We sleep researchers are incredibly creative, so we have REM sleep and then we have non-REM sleep. So we have the two things. And then non-REM sleep we can subdivide into different sleep stages, and a portion of that is then light sleep versus deep sleep. But then and deep sleep is also slow wave sleep. But let's go through them. So imagine, or rather not imagine, because then you're going to fall asleep now, but roughly imagine it's now evening, you're going to bed, you're falling asleep, so you'll have this 8-hour time period, which you can see depicted up here, which we can now score and look at what type of sleep you have. We score sleep by looking at 30-second time windows, so this is a 30-second time window where the green is the eye movement, the black is the EEG, so the brain, and then the brown is the muscle, and in this case we also have a heart rate, so that's red. Because actually, as you could see, so for sleep state classification I just need these 3, but you'll see here this is more actually of the clinical setup where you also have number one, this thingy actually measures in which position you are. So if you're lying on your back, on your side, or anything, then you often have these straps. You will have a second one on your stomach that can measure your breathing. And then you have a little, this is the airflow underneath the nose. It's for the airflow. There's a microphone here, that's for snoring. But so this, and then those are just the eyes and the head and the chin. And then you can also sometimes, depending if it's a clinical one, you will also have electrodes on your leg, because we have the classic leg movement disorder where you move your legs at sleep and everything. So if you want to know that stuff, you need, of course, additional electrodes. But we don't do that in research usually. But we do the heartbeat, because your heartbeat also will change throughout sleep. So now you're falling asleep. Your EEG actually is looking quite similar to wake. So it's stage 1. So this is stage 1 sleep. This, as I said, we transition via stage 1, and stage 1 is not really a sleep stage. It's kind of just, it's really short. It usually only occurs kind of on the transition. It's just because your brain hasn't really decided yet what it's doing. But we can recognize that you are sleeping because, number one, usually when you close your eyes and you're relaxed, you're going to have a very strong alpha oscillation. So that's 8 to 12 hertz oscillation. And that disappears. That's how we know that you're sleeping. Further, there's something that you not always will have, but you sometimes will have, and that are slow rolling eye movements. So that's what this here is. So this is the eyes that are slowly starting to move. And the funny thing is, in this sleep stage, almost everybody will tell you they're awake. So you haven't lost consciousness yet, because consciousness and sleep are two different things. You could retain consciousness and be asleep. I was just saying, you could lose consciousness but not sleep. Of course, that's coma. So that's why they're two totally different things. Usually they correlate, but they don't have to. And so the funny thing about this is I've gotten to the point where I notice my eyes roll. And then you're like, oh, cool, my eyes are rolling. Oh, I'm awake. And then you're like, okay, let's try this again. So it's part of me, like, watch yourself. You can find this. But at the same time, don't do it because you're going to create an insomniac out of yourself. So don't, who knows? Maybe you'll notice it at one point. So then after stage 1, we go deeper into sleep. We'll now go into stage 2 sleep. And that's the actual, what you would call now proper sleep in a way. And now stage 2 sleep is the one thing that none of you really mentioned. Okay, but that's stage 1, 2, 3, 4. Stage 2 sleep is in a way your main light sleep. And maybe that you've heard of. And the joke about it, this poor neglected sleep stage is being ignored by the general population. It's being ignored by researchers who like to focus on SOIC and REM sleep. This is 50% of your sleep. This is the most important sleep stage that you will ever have. And for some reason, it's just not as fancy. It doesn't have the fancy of rapid eye movements. It doesn't have the slow wave sleep. So somehow it's being neglected, which I think is a shame, because it's such a pretty sleep stage. And the way how we can recognize it is that we have what we call sleep spindles. These are these things. This is what I also call the dirt on the EEG, because in human EEG it looks like dirt. And actually sleep spindles are these short, they're 1 to 2 seconds. They have roughly 15 to 16 hertz. And if you would filter them in just that frequency range, you would see that there's this beautiful waxing and waning shape. So they're very pretty. And another thing that we have is here. This is a K-complex, or an individual slow oscillation. So what I showed you before about all neurons being synchronized and regularly firing and being quiet, that would cause a regular delta wave or a slow oscillation. This is just an individual one. So this is suddenly a lot of your brain, I mean not the whole brain, but a lot of neurons in your brain turning off together, and then they turn on together, and then usually what you could see kind of riding on this is what we call an up state, because it's more activity in the brain. There you could see then the sleep spindles sitting there. And so this is an oscillatory coupling that we actually like to see a lot in sleep, which will come up later when we look into what is important for memory, is exactly the slow oscillation, the sleep spindle, and then there is this other oscillation which we can't see in the human yet in the surface, which is the sharp wave ripple. And the sharp wave ripple sits deep in the hippocampus and is very, very important, but we'll get to that later. Yeah.
Do this phenomenon, rapid onset spindle, have a specific frequency?
So of course, we have, of course, different ways how we can define frequency. So we can define frequency in a way of the event itself. So if I just filter what happens, and then yes, this is 12 to 16 hertz, this is 0.5 to 1 hertz. Then, of course, you also have the frequency of occurrence. That is not that clear because it's not as regular. Then there's an additional really macroscopic organization where you see the frequency of these bouts. So you could see that here's an epoch where you have more of these kind of effects, and then you will have other epochs where you have less of this, and that's organized on the 0.02 hertz frequency. And now there's even newer research, but that we really don't want that. There's probably even a 24-hour regulation of it. So that's the beauty of all our stuff. Everything is organized on different time levels in oscillations, which us sleep researchers love. Yeah, I love
Classification of 1, 2, 3, 4 is done automatically?
No. So the hilarious golden grail of sleep research. This is all human scoring. So humans actually have to score the sleep stages. It has not been managed to be created automatically, even so it's, as I said, the holy grail of sleep research is, because it's so many man hours go into this, that you have a program doing it for you. The problem is, while within a person this stuff is very, very, very stable, between people, especially when it comes to disease, also you're getting higher variability, so classifiers don't work. So we cannot train any computer program to actually automatically stages. But people are working on it.
It will be classified by two different people or just one?
Classically, you will, when someone learns it, it has to be two people. But these data are sleep scored by experts who have been sleep scoring for 30 years. And they don't do anything else but sleep scoring. And so only one person scores, because it's too much. It takes 2 hours to do a night.
What was the importance of the third recording, C3, C4? Is
So,
between left and right difference?
Yes. So even numbers are always on the right, and odd numbers are always on the left. C is central. And so we have to decide which sleep stage it is. Classically, you use rechtschaffene chaos, which was created in the 50s. And they only ask you to record all your criteria are dependent on C3, C4. However, there's a newer criteria that were published 2012, no, older. 2009 or something, we got new criteria that not everybody uses from the American Association for Sleep Medicine. And they now want you to record F, so frontal, C for central, and O for occipital. Because there are certain oscillations, so these slow oscillations you can see better in the front, while there are other oscillations you can see better in the back. And so that's why they have this diverse course. But it does make a big difference, that's the irony. Huh? Okay, good. So this is stage 2. And as I said, this is all continuum. It's not, I mean, we pretend as if these are abrupt cuts between sleep stages, but actually this is very fluent. So in rodents, I also sleep stage. When I score smaller epochs. So I score up to 3 second epochs. But when I go from stage 2, usually what I'll do, I'll transition into stage 3. Stage 3 is in a way already part of slow wave sleep or deep sleep. So it's the, it's just what we think of deeper sleep. And the main reason how we classify it is we still have our spindles, we still have our slow oscillations, but now we start having what we call delta waves or slow waves. So these are 1 to 4 hertz oscillations, and they usually occur then more regular. So while these the slow oscillation itself, which is 0.5 to 1 hertz, is more of an isolated event. These are these salves of a bit faster, so that's why 1 to 4 hertz oscillations. And that's then and if we have 30% of these, that's when we call it stage 3. If we have 50% or more, that's what we call stage 4. So this subject is still my favorite. That's why I use her. I even know who it is. I use her EEG always because, I mean, she was one of the best slow oscillators I've ever seen. Because I think that's quite amazing to see those huge waves. I mean, especially if you're used to the wake stuff, which is really tiny, to see this is quite beautiful. And so as you can see here, and as I said, for the non-REM, we've been now mainly using the EEG. The eyes don't really do very specific thing. The muscle as well you can be slightly tense, you can be relaxed, whatever, anything can happen in a way. Yeah.
What's the percentage of phase 3 and 4 in healthy volunteers?
20 to 25% roughly.
Combined?
Combined, yes, because it's deep sleep. So roughly, in a way, you have 50% light sleep, which is mainly stage 2. Then you have 25% roughly of deep sleep and 25% roughly of REM. But it will be individual. So some people, I call some people the REMers. They have a bit more REM, but less deep sleep. And some people are the deep sleepers. They have more deep sleep and less REM. And then generally when you age, how it changes. So you start with, as a kid, you have way more, so babies have almost 50% REM sleep. And then the REM sleep proportion goes down to 25% kind of over the first couple years of life. And then afterwards, it stays kind of stable. There are some, but it also depends how you analyze it, that it goes a little bit down, let's say from 40, 50 onwards, it all starts declining a bit more. Deep sleep, similar thing. It's kind of stable, and then it slowly declines, but not much, actually. So it's declining less than people think it is.
It changes during the night?
It changes during the night, but that'll come up. That's one, next slide. Because of course we're now at the end of our non-REM. What comes next will be REM. And I think you don't need to be a sleep researcher to tell me that this is something different than this. I think you see that? So REM is the very famous sleep stage, which was found in the 50s. Ironically, it actually has 2 names because the French found it at the same time as the Americans. The Americans focused on what we could see here. Those are the rapid eye movements. and this really quickly looking around. And that's why also if you watch people, you could see the eyes move under the eyelids. And so that's why they called it rapid eye movement sleep. The French were a bit different. The French focused on the fact that the brain looks awake. So looks almost like awake brain. It's desynchronized, small amplitude, fast frequencies. And so they call it paradoxal sleep. And they still call it paradoxal sleep. So it's kind of funny. You could see in the papers, you don't have to look at authors, you can always see where they come from. If they're American influenced countries, they will call it REM sleep. If there are French influenced countries, they will call it PS. And PS is paradoxal sleep. Same thing. And so exactly that, of course, gives you a problem when you're sleep scoring. So when you're sleep scoring, you now have an EEG that just looks awake. There's no obvious difference. I mean, it's a bit less noise, but it generally looks awake. The only way how you can recognize if it's REM sleep in comparison to wake is by using the muscle. Because the rapid eye movements, yes, they will occur, but there will be, of course, long periods without them. Also, before they first occur, you can backward score that it's REM sleep. And the one way, what is 100% reliable, is that you are totally atonic. So you're paralyzed during REM sleep. And there is a reason. Or we believe, so we don't really know. So the only way we know that there must be a reason is that there is one disease where you do not have this REM atonia, and that is the REM movement disorder. And now REM movement disorder is kind of a not really weird disease, but it's a sad diagnosis to give, because most people who have a REM movement disorder, it occurs usually in the 50s and 60s years old, will be the first diagnosis, and usually men. And then most of these, or many of these patients will go on to develop a certain type of dementia. So it's often the first symptoms for example, Parkinson's disease, as well as similar Lewy body dementia, et cetera. So the dementias that are based on a certain type of pathology. And they will often start, or not often, some of them will start with a REM movement disorder. But the interesting is how it actually gets diagnosed. Because the REM movement disorder, you don't notice yourself. Because like almost all of sleep medicine, you don't really treat the person who has the disease. You actually treat the bed partner. Because in REM movement disorder, the classic story will be that a lady will come and it can maybe take a few years actually, and then start complaining that my lovely husband, who has never, ever screamed at me, is beating me up at night. And that's something that is often hard to talk about, because this is a different person. And of course it is a different person, he's sleeping. He's not aware of what he's doing. And it's a weird thing that it turns out that people who have REM movement disorder, they tend to have more violent dreams, and they live out their dreams. And that's the problem. So that's why this atonia is very important and is very good. And it's kind of funny because there are a lot of epiphenomena in sleep that you can explain through the atonia. So have any of you woken up with paralysis? Yes, because it does happen. I've done it once, that I woke up and then I couldn't even open my eyes. So I was totally paralyzed. And then don't panic. It's just that your switch wasn't, your brain was faster than your brainstem. And so you could just wait a bit, fall asleep again, if you wake up again, your paralysis is gone. That's the leftover of REM. There are also little funny stuff. So, okay, if we can, dreaming is a whole different topic. Dreaming, we don't know anything about, to say in short. But there are some things, sometimes you can find things in dreams where you realize it's your brain trying to make sense of what feedback it's getting. And so for a classic one would be, the monster is hunting you and you're running through like mud. So the legs are not moving. Your brain is getting the feedback. You want to run, but your brain is getting the feedback. You are paralyzed. So that's why this is your brain trying to bring together the body feedback that you're paralyzed with the urge to run. And that's why you're running through mud. So that's at least what we think. We don't know. I mean, dream research is very subjective, so it's can't really look into it. But there's all this kind of fun little stuff. Now, funnily enough, if you would ask about sleepwalking, because that's, of course, the other classic one that everybody knows, sleepwalking is deep sleep. And it's not REM. So in REM, you're paralyzed. Sleepwalking is deep sleep, yeah.
What would you measure, or what would you see if you're not sleeping, but you have a nap?
Same thing. A nap is sleep.
So you could have
Which phase?
in a 10-minute nap, you could...
Haha, yes. So we'll go, yes, the sleep phases. So what we just did was a non-REM-REM cycle. So we have just brought you through a non-REM-REM cycle. And as you said that, we said when you fall asleep, you go through stage 1, 2, 3, 4, and then those 2 are deep. The first 2 were light sleep. And then afterwards, usually transitioning via stage 2 sleep, you're going to go into REM sleep. So this is a non-REM-REM cycle. Non-REM cycles are always fixed in length for a specific person. So if you can be a 90-minute person, you can be a 120-minute person. But usually your individual non-REM cycle will stay the same length forever. And you will have repeated of them. And the repeats will be usually between 3 to 5, depending if you're a 120 minutes person or a 90 minutes person. And that's why maybe you've heard of the general tip of sleeping a multiple of 90 minutes. Some people have heard about that. That comes from the non-REM-REM cycle. Because the idea is that what we did to this subject, that I woke him in the middle of REM, is evil. Because waking out of REM is like, ugh. And while waking up out of deep sleep is more like this, what? So that's my impressions of waking up. No, so the easiest way of waking up, or the nicest way of waking up, of not having this groggy feeling or this disorienting feeling or something like that, is waking out of light sleep. That's why a lot of these apps that pretend to help you with sleeping and waking up, they're really tricky, because what they just do is usually they will measure the movement of the mattress, so your movement. That's why they don't work with 2 people. Yeah. And then they will, and what they do is they measure, they wait for the no movement period, which is your REM sleep, and then afterwards they will wait for the first movement after no movement. Because then that's usually you being in light sleep after REM, perfect moment to wake up, you won't be groggy. That's how they hope to work. I don't know if they work, because I don't have one. But and so, yes, so the non-REM cycles will always be the same, and that's why you just have to find out your personal one and then always sleep in multiples of that. And the sequence of non-REM and then REM is always the same. It's always like that. We go to mice and rats, always non-REM-REM. They have exactly the same kind of sleep cycles, and because there's only one exception again, when REM comes first. Now, do you know that exception? Because actually, probably most of you do. It's the one sleep disease that is very famous.
Narcolepsy?
Yes! Narcolepsy. Narcolepsy is the only time that where REM sleep will be onset, where you can start with REM. And that's the disease, of course, of narcolepsy. Now, narcolepsy is, I call it a funny disease, because it is a funny disease, because you can make people laugh and they collapse. That's funny. They usually are, no, that's funny. So people study what they have problems with. I'm an insomniac. I know narcoleptics because they're sleep researchers. It's really funny. A lot of sleep researchers are actually sleep diseased, so that's why you actually know these people. And so narcolepsy, there are different portions, of course. It's called cataplexy, that they really have this. One of the problems is that if you make them laugh, they lose their muscle tone and fall asleep. And so there are these hilarious YouTube videos. So just Google narcolepsy of friends of narcoleptics who film their friends. There's one where it's an evening with like 6 teenagers, and the boys are evil because they the whole time make their friend laugh, and so their friend is collapsing the whole time, and they're filming it all, putting it on YouTube, and it looks really funny. And he seems to have fun. I mean, he's laughing. So he wouldn't collapse if he wouldn't find it funny. So.
Until he hits his head, of course.
Yeah, they're used to that. They tend to, the funny thing with narcoleptics, they tend to not hurt themselves. We don't know why. They really collapse like this, but they just tend to not hurt themselves. But yeah, so the narcolepsy is for one thing that, but narcolepsy also, for why I like it so much, is it's such a cool, in a way, success story of medicine and of research. Because, do you know the cause of narcolepsy? We do, actually. So the cool thing about narcolepsy, up until like 10 years ago, we knew nothing. It was this random disease where people would collapse and we don't know why. Now we know that you start off having a flu. Thanks to having the flu, you create some people who have a certain genetic predisposition can create an autoimmune disorder. So this is similar to like diabetes type 1 or thyroiditis or anything like that. All these diseases are autoimmune diseases. So you creating an antibody against yourself because you're attacking actually a flu or something. And then these autoantibodies attack a certain brain area and destroy the orexin or hypocretin, because again, two labs found it at the same time. They called it orexin, they called it hypocretin, but at least the brain area that produces this neurotransmitter is destroyed. And so you don't have that neurotransmitter anymore. Through that, you cannot keep sleeping. Because it actually turns out that not only fall asleep during the day, they can't actually continuously sleep during night. So we've gotten from no idea what it is to a complete story. We know how the disease happens. And the problem is currently it doesn't really help us treating. But at least we know how. We can know where to start and go in. So it's a true successful story of science. And again, if you want to see funny videos, Google Stanford dogs. Because this is all done in a dog model. And so these are the Stanford dogs that collapse. And they're really funny because the dogs run around really happily, and when they're happy playing, that's when they get narcolepsy. So it's kind of cute. But okay, narcolepsy. Going back to the sleep stages. So as I said, we have our non-REM cycles. And in humans, we tend to sleep, so as I said, we have 3 to 5 of them per night, and then we tend to have, let's say, 8 hours of sleep, and usually during the dark period, because we tend to be monophasic as humans. And if we go to the rats, so mice and rats, that's what I like to work with in my research. Again, they're the perfect model, because they have non-REM, they have REM, they have the substages. The only thing is usually we don't subdivide non-REM, we usually just take it as a one thing. Then what is different is that for one, while we are monophasic, or some of us are biphasic, so you have a main sleep plus you have a nap. We have so rodents are polyphasic, so they go in and out of sleep really, really often, and their sleep bouts are way shorter. And another difference is they tend to be more day sleepers and night active. So they sleep during the light on, and we sleep during the light off. Now, naps, I was to bring it up. So what you sleep in a nap is usually dependent on what you sleep deprived yourself before with. But if you are normally sleep deprived, or a normal sleeper, you will in a nap go exactly through a non-REM cycle. That means if you have a 10-minute nap, you're only going to have light sleep. If you have a 30-minute nap, you're going to be lucky, you may have some deep sleep. 45 minutes, yes, now you're having deep sleep. Minimum 60 minutes, so that you have to have a non-REM thing. And that's how the different naps go together. And we also brought up the different sleep stages across the night, and you can see already here that there is a difference. Because while the non-REM cycle in itself is the same and will stay the same length, the proportion of the different sleep stages in the cycle will change. So initial sleep will be dominated by the deep sleep stages, so that's the 11 o'clock sleep in a way, while the early morning sleep will be more dominated by REM sleep. Of course, what is late and early is dependent on when you go to bed and when you get up, and that we're going to get into right away. So that means I say 0 is your time going to bed. It's not world time, okay? So if you suddenly go, like, especially if you do sleep hygiene, so sleep hygiene means going to the bed at the same time, getting up at the same time every day, because that's healthy. And then, yeah, also other things is like don't do anything in your bed but sleeping. But if you do that and you suddenly go to bed 2 hours later, and if you're really well trained, you actually will just skip the beginning. You will just skip the deep sleep stages and then always go sleep more here. Well, it's the same thing other way around. If you suddenly get up 2 hours earlier, you're going to selectively REM sleep deprive yourself. This is, of course, also a difference in age. Young people are usually tend to be better with shifting, so they can randomly. I noticed it clearly when this started happening, so that when I would go to bed 2 hours later and I just felt like I never really slept. And that's just because we tend to be good at losing consciousness during deep sleep. And if you skip the deep sleep, it may be that you feel the whole night that you were awake, but you actually were sleeping. And you notice the next day because you're a bit less tired than you should be. Because that's a general thing, the sleep being, so when do you lose consciousness? I would say the majority of people lose consciousness in stage 2. I think I belong to the people who lose consciousness sometime in deep sleep. I sometimes never lose consciousness during sleep, and this is really annoying. That's why I have insomnia, because then it's really exhausting to be conscious while you're dreaming. But that's why, yeah, you tend to lose it at some time, usually in this transition, but anybody can lose it differently. Any question on that? Good. Because one thing I was just saying, so that what your zero is a very personal thing, because some people will feel very much recognized in this picture. Some people not so much. I'm that. I once had a relationship. Oh God, that was horrible. Yes, because the boyfriend Lark was even forcing me to go to bed at. Oh, it was horrible. It's exactly that. Because we do have chronotypes, and there's a reason. Evolution has made the human species adaptable by creating diversity within the species. That's something what I think is very important, which most people don't realize in a way. What evolution, you always think about an individual person. No, we as a species have managed to become adaptable. We don't need generations to adapt, because we can adapt within the generation because we have a diverse mixture in brain, in everything. And one of them is this, because we can conquer the day by having a spread across in a way when is our perfect functioning moment. Because now the first question is, when you go to bed and when you get up, we're going to now do a screaming match. Call nail hours. I want to see, when you go to bed?
10 o'clock.
Midnight.
12 o'clock, 2
Midnight.
So we now already heard a variation of almost 4 hours. Then when you get up, okay, that will be roughly the same. What's the earliest? Does someone have a 5?
5:30.
Oh God, the larks, or kids. There are 2 ways how you can recognize when someone gets up, lark or kid. Who gets up after 11? Oh, yay, we have someone. See, again, we just created a variability of 6 hours. That's amazing. Is there a difference between your free days and your working days? I can tell you that probably the people who are a little bit earlier will say, no, not that much, no. The owls were like, oh, yes. And then you remind you of your school times, and then the owls will scream even more. But yeah. And then the biggest question of, do you use an alarm clock? Hands up for who uses an alarm clock. All of you be ashamed. You're all sleep deprived, chronically. Worst invention of humanity. I do not use an alarm clock. I mean, I have a backup one for certain times. I also don't make appointments before 10, so. I'm a university professor. I mean, come on, I can. But yeah, so the reason all of this is important is because there are 2 things that influence your sleep. The one, so Borbelé, hidden behind the thing you can see, it's Borbelé, the famous, in a way, godfather of sleep from Switzerland. He proposed the process S and process C. So process S is, in a way, your sleep pressure. The more you stay awake, the more you build up your sleep pressure, the more you want to sleep. So you build up sleep pressure over the day, you fall asleep, it goes down. You build it up during the day when you're awake, and it goes down. But there is this additional modulating factor, which you have may noticed if you stay up for long time periods, that actually how tired you are still varies. That is process C. So process C, of course, is circadian. And the process C will have, for each person, will be individual, and will give you certain times where in a way, it's also about the difference. So that's why are less tired, and then you become more tired or not. And then you can see that if you would now skip it, so this would be the prediction of this model. If you skip a night, so here you skip a night, that you would have bigger problems falling, so you would feel more tired, especially in these early morning hours, but then around noon, you would actually lose a bit of that tiredness, and then you would get stronger again throughout the day. And so we, of course, try to manipulate with process S and process C, and we have a lot of drugs to do that. So, of course, adenosine is the molecule that is doing the process S. And we all love our adenosine antagonist, coffee. And so that's how coffee works. It works on S. While the other one, and this is now becoming more popular, this is everybody uses, of course, but more popular is, okay, light is what actually entrains your process C. And nowadays, because we have the problem that our light exposure, instead of going like this, as it should, it's now like this. So it's just us being in these rooms with artificial lights that don't have blue, and we need the blue. That's why we don't have these big fluctuations in light as we should have if we would be working on the fields and being outside the whole day, hunting our mammoth and whatever not. And that's why we have all more sleep problems. It comes from the light. And now this is one of the big new things in sleep, so we give now melatonin, and it's really good for if you have jet lag or something. So if you have sleep problems, this is something. It's very, very subtle. It doesn't change your sleep. It's currently the best we can give for sleep, because most drugs you would give for sleep actually make your sleep worse. So all the classic benzodiazepine and everything, they destroy your sleep, while melatonin really is just going into the regulation, so seems to be working well for that. It's not so strong, of course. And how important that is, because if your chronotype is not static. Number one, it's personal. Everybody has their own chronotype, but it also changes throughout your lifetime. So this is a beautiful data by Till Rönneberg. This is actually old. This is from 2004. He now should have twice the ends. These are roughly 150,000 people, but he now has data, I think, from 500,000. It didn't change much, but and so what he could show perfectly. So he looks at your chronotype. He doesn't want to call you an owl or a lark, because those are the two extremes. He gives you a variable where you can create your MSF. If you want to create your MSF, go to his website. It's the Munich Sleep Chronotype Questionnaire or something. MSF is very simple. Let's see, I go to bed roughly, I actually sleep a lot, so this could be embarrassing. I go to bed at 12, I get up at 9, so my MSF is 4.5. It's the middle of the night, of your personal sleep night. And he adapts it, so that's why SC is corrected for oversleep, because he takes the weekends when you actually should be more your chronotype, and SF, because us owls are chronically sleep deprived, so he corrects for that a bit. At least what you could see if you look at now your chronotype, so up is late, is that when you're a kid, you're really early. And anybody who had a baby can prove that. They're really early. And so when they are very early chronotypes, and then you become later. And ironically, the flip is exactly the end of adolescence, but this is the first best biological marker for the end of adolescence. So it's roughly 18.5 for girls, and I think 21 or 22 for boys, because yes, women are grown up earlier than men. And then you become earlier afterwards again. And so there are, of course, a lot of fun ways you can interpret this. Why did biology accidentally, or why did evolution doesn't make, but why did this happen in evolution? You could argue that the old people take care of the kids while the young people hunt. Because what the chronotypes give you an advantage, or not, I'm probably not going to even talk about memory ever. We only talk about sleep today. But because I never know, my anecdotes, you never know how long it talks. So the one thing about late so the early types, and I notice this a lot in our labs, which is really funny. So late types are good at skipping. Because what you so skipping a night, skipping sleep, because what makes you a late chronotype is that your internal clock is longer than 24 hours. Well, if you're an early chronotype, your internal clock is shorter than 24 hours. And so the early types, if you watch them, they really crash at 5 p.m. They really cannot work much afterwards. For them, if they suddenly have to do a night shift, something like that, they're really bad at that. Late types are really good at jet lagging. They're really good at switching shift schedules. They're better at just suddenly skipping a night. For that, as I said, regular 8 a.m. meetings like school is a nightmare. But for everything else, that way, that's the better at. And so in a way, it gives you the adaptability. So these people were the best at lying there still in the early morning or late night, trying to wait for the animal to pass and not fall asleep, even though it's boring. And so these would be the perfect, when you have your perfect level of fitness, is exactly when you have the latest chronotype. So that's why the hunters. That's at least from Till Rönneberg, the suggestion. Of course, yeah?
If we
understand well, in early times the women also hunted.
Yeah, okay, yes, but number one, at the same time, there is a gender difference, so where women on average are earlier. So you could, of course, argue that that's also why the men are later, because they are then the hunters. But of course, they would be the gatherers. They're still the ones who have to maybe walk very far, and then that's why they take longer. He only explains it with the men in the book. But there are some fun ones. So I'm going to do some anecdotes that he likes to do with his slide. One anecdote is, so you know that on average, women tend to look for partners that are like 4 years, 5 years older. That's exactly so that they end up with the same chronotype. That it's true. I mean, the most extreme couple I've witnessed was actually the parents of also an ex-boyfriend of mine. She was a really late chronotype. She would go to bed at 3 a.m. and sleep till 12. He was a really early chronotype. He went to bed at 9 p.m. and he got up at 4. So they overlapped in bed for an hour. They still had 30 years of good marriage. Maybe because of that, okay. But yes. So that's why you can have a lot of fun ones. I mean, where am I? But of course, everybody has their own variability, and I'm, for example, on the higher. I'm anyways more of a late chronotype. And the main reason why, especially sleep researchers tend to be late chronotypes, because we all suffered, because society is made towards early chronotypes. The average time to go to bed in Western society in Europe is between 11 and 1 p.m. or 11 p.m. and 1 a.m. The average time to get up in Western society, if we wouldn't have social influences, would be between 7 and 9 a.m. Most offices expect you to be at work at 8. That's when you should be getting up. So that's why we are all chronically sleep deprived. And this is what so Till Ronnenberg calls the social jet lag. Because ironically, if you look at it, if you look at the amount sleep duration, you will see that the average sleep duration is, let's say, 7.5 or something hours at work days, and you have shifted to more sleep at free days. This means that you are sleep deprived during this period, and that the average is different, so that it's not the average across all. That's what it should be. And then if you actually look at how sleep deprived you are, so how much do you sleep, according to which chronotype you have, you see that there is a difference. So if you are this is this is weekdays. Yeah, weekdays is black, weekends is white. So that's how it is. So you see that the thing about it, actually, if you're an early chronotype, you sleep enough during the week. But as soon as you become in 4.5 is, what's the average? 3.5 to 4 would be the average Western person. But as soon as you are longer, you're actually getting chronically sleep deprived during the week, and you're trying to catch up with this on weekends. That's what it is. Ironically, really early chronotypes, they're sleep deprived on weekends. Because really early chronotypes are fine with getting up at 8 or getting up at 7 or 6 or 5 to go to work. They have problems when they suddenly have a social life that goes to 11 p.m. or midnight. They have problems staying awake. And so they're actually chronically sleep deprived, ironically, on weekends. But this is the reason why there's this big thing, and now also changing that finally, hopefully summer, winter time will be abolished, because that also is really bad for sleep. And so this is all the things where finally we have to change this stuff. And that's why also Till Ronnenberg is now going on the barricades, because they want to stick to summertime, and summertime would make this worse. And so that's why you shouldn't do it.
Is the standard deviation?
Yes, so you could see that normally he doesn't even have one, because his sample size is so huge. The hour is over.
It's memory.
Memory.
15, 20 minutes if you're okay with it. So
Are you okay?
sure,
Good. Sorry. As I said, it's hard for me to estimate how long stuff takes. This talk usually takes, it's 30 slides, it should take 30 minutes, but okay. Okay, memory. So let's talk about memory a bit. We're going back to our neurons, because what we believe is memory is is actually a cell assembly. So it's a network of neurons that when they're active together during learning, and when the same network of neurons is active together during some point later, you're going to remember. So that's your memory. That's the encoding of that. And we have certain brain areas that are really important. So that's the hippocampus, especially for early learning. And then later, when you're on the long term, you're going to consolidate it to the cortex, especially the prefrontal cortex. But of course, it's not only there. Actually, this is a network. So this network of neurons that's active together is spreading the whole brain. It's not like, oh, that's where the memory sits. No, the whole brain has the memory. And individual information will be in specialized brain areas, like visual information maybe will be in the visual cortex, auditory information in the auditory cortex, motor information in the motor cortex, etc. But the main thing that these two brain areas do is that they are these hubs in the network. So they're binding everything together. They're what strengthens it all. And as I said, initially you're going to use the hippocampus. And when we use the hippocampus, so the hippocampal memory, if that's the one that actually initiates recall, what you're going to remember is an episodic memory. So an episodic memory will be something with all the little details, so all the smells, the sounds, and it's going to be the event you will remember. For this, for example, you're going to remember that I stood here, that I wore, and I had this sign, and then I made jokes or whatever, and then some detail, maybe I'll remember my earring or something. So these will be all the details in the episodic memory. In contrast, when you consolidate it to the cortex, the long-term memory, you don't want to keep all this, so you're now going to abstract it. And so you're going to remember the gist in a way. So for example, if you would take this lake, after all these visits to the lake, you're going to have a spatial memory of the lake. You're going to know where the trees are, where the parking area was, where the best place for a picnic would be, so that in the future you can navigate very easily around there. So hopefully, for example, out of this experience, of course you only have one, but you're going to come out, you're not going to remember all the details, how I stood, what I was wearing, but you're going to remember maybe, okay, she was generally trying to make jokes, she made herself a little bit silly, and hopefully you're going to remember that's some information about sleep and some information about memory. But you're going to remember the gist, not the detail. But again, it's not always the case. While we most of the time want to build up these gist memories, sometimes we want to keep this in very detail, and that's if something really surprising happens. There's a bear attacking you in the middle of a lake. And the instance of like this, these are unique events. This is when something happens that you've never experienced before. And the problem what your brain has there is that if it would now consolidate this to the cortex, it doesn't know what it should consolidate. Because how your brain usually decides to consolidate is it will compare different instances. And it will see which information overlaps between these different instances. But if I have a unique memory, I can compare it. And then but at the same time, these unique memories could be very, very critical. I mean, if I survive the bear attack, I really want to know which information I can use next time to predict a bear coming. So it could be that the birds were suddenly silent. And then you want to, next time you're in the nature and birds become silent, you want to be like, oh, bear, run. And this, of course, to give you examples, luckily, this doesn't work in student courses that well anymore, but it will work here. Most of you will remember where you were 9/11, 2001. It's been a while. But yes, you will remember on that day what you had for lunch, or you will remember unimportant details. That's because you had a novelty event. It used to be easy because we had 9/11, we had the Berlin Wall. If we go even better, or actually my mom's generation, because they had good communal memories, because they had the moon landing. Everybody knows where they were at the moon landing. And those are these events. Sadly, social media has destroyed this. We somehow, I don't know how, but we don't have global novelty events anymore, so 9/11 was the last one. I mean, I have the Trump one, so I do remember. I will forever remember when I realized that he won the fucking election. But not everybody will have that, but nowadays you still have the personal ones. So you could still, one student of mine gave a great example. He said that you will go for dinner with your friends really often, and you will maybe remember the food was yummy, but you won't remember a lot of details. The one time your friend's kitchen started burning during dinner, you're going to remember everything. So that's also, or of course weddings and anything like that. Those will be the stuff where you remember a lot of details. So that's this in a way, and that's a different consolidation effect than sleep. But let's go back to sleep. Because what actually happens during sleep, and this is now the cool thing. I told you about the K-complex and the sleep spindle here drawn very comically perfectly. And during these oscillations in the cortex, if we go to the hippocampus, what we see is a sharp wave ripple. So the sharp wave ripple is this really fast, really short oscillation. It's 150 hertz, goes for 100 milliseconds. And what you see during this oscillation is a communication between the two brain areas where memories are reactivated or replayed first in the hippocampus and then later on in the cortex. And by reactivating different types of memories, you can now uses to abstract information from multiple events. So that's what we do, what we think sleep does. And so how do we know this? We mainly know this from using rodents, because I told you before, this is the hippocampus where we have to get to. The hippocampus is deep, deep, deep down there. It was really hard to get to in humans. And so what we could see in rodents is that we have this great phenomenon called place cells. So place cells are so amazing, they got a Nobel Prize 2 years ago. And so, no, 3 years. 2014, oh God, it's been like 4 years now. And so the place cells, what they actually do is so these are in the hippocampus, and if this cell, for example, will always fire specifically on this space, so this place in the world, that's my place to fire. And then, for example, cell 2 would always fire on this place, or cell 3 will always fire here. And so if an animal runs along a track to get to the chocolate, he will have the specific sequence of neurons firing. And what we can then do is we can actually look at what happens when he's eating or when sleeping, and what we could see is that the same sequence gets fired again. But it fires at a way faster pace. So you're firing now at 7 to 10 times faster your experience. So your replay, which also as I said happens during wake, you're not aware of. So you may be replaying now like crazy, because maybe you're sleeping, I don't know. But you may be, but you won't be, it's not like you're gonna notice it. It's not like it's things shooting through your head. So you're consciously not actually progressing this, but this is still what makes you think. And to look at this in more detail, these are amazing videos from a different lab, and I'll explain them as they go to save on time. It will be a lot seen. But you'll see, so this animal has an implant. Every click is a cell firing. You'll see here they coded every cell with a color. And as you see, when the animal is once there, the cells will fire. So this is a different way of plotting, so we can differentiate these different clusters, so the different cells. And what you'll see while with the animal running is that it's not as simple as I just showed you before. So it's not like the blue cell only fires here. I mean, it also fires here. Here's now total craziness, but we'll just ignore that. And I'll explain it later. And so when you go across it, what the main thing you'll see, again, blue one is again here, the turquoise one here and here. But one thing you may already notice is that the unique combination of cells, so what we call a cell assembly, that is what's going to make a space totally unique. So like here, it's the combination of the two, the combination of the cells, which will be make us able to actually use the neural data to predict where the animal will be in the real world.
The place cells are located in the hippocampus or not?
Yes.
Yeah?
Yes. Place cells are in the hippocampus.
Special in that fact that they keep a map of their vicinity in their brain.
So yeah, so the discussion of if place cells are actually place cells and if this is a cognitive map is a whole. So we thought we all knew it, and everything is totally true. It's currently a mess. But most likely, actually, we don't call them. I mean, I don't call them place cells; they're event cells. But so they are actually a coincidence of what's happening combined with where you are. But that's very future. For simplicity, we're kind of leaving that out.
Yeah. Conclusion is the humans.
So we know that place cells, where we can find them. So place cells have been shown in humans with these patients. We've seen them. So we now know that this system is totally conserved. Every mammal has the same system. And it's, of course, just not only the hippocampus. You also have grid cells in the medial-entorhinal cortex, and then you have like border cells. So you have cells that will selectively fire if you have a border. You have cells that selectively fire in which direction you're looking, et cetera. So there's a really complex system of a lot of very specialized cells, which together let you know exactly what's happening in a way in the world.
All hippocampus cells.
No, they go. So there are also brain areas next to the hippocampus and the head direction cells, which seem to be actually way more crucial than everybody thought actually exist in many. So they even go, I think, back down almost to the brainstem. That there is, I think, so the because it's not really my forte, but it's, I think, supramammillary body is, because that's the on the real bottom of the brain. So it is, I think of it as a whole brain thing usually. The hippocampus is just, so everything is usually found in the hippocampus because people like looking at the hippocampus. So it's just a very common brain area to focus on. So now the next video, what you'll see now is that we're going to they use now the brain, this neural data to predict where the animal is. So no video, so the computer program is now only using neural data, so it's not using the video. And as you can see, the program can now, so you train it up, and then afterwards it can exactly tell you where the animal is on the track, which direction it's running. That's only because of the linear track of it. And so you see red versus blue. And how large the error is telling you how quickly it's moving. And so you can see that this program, it works quite well. But sometimes, like now, craziness happens. Oh no, it's broken. Crazy. And of course, this is not the classifier malfunctioning. It's just the problem that this is way too fast. So the last video...
We had to get the food at A or B?
At both, always at the end.
Okay.
Because maybe he has to walk back and forth. So what they do now is that they take these moments where the animal's not moving and they slow them down. The problem is they only slow them down by 1/5 and it's way too fast. So you will see me try to explain it really, really, really quickly. So they have 3 different versions which they're trying to decode in a way. So this is going to be replay. So this is first, I think, how did I get... Now, where am I going next? Now he's going to think, how did I get here? And I think then now, and then, yes, this is... Huh? They should have done it slower. But this is trying to show you replay. So you could see that this animal was in a way thinking these things, because often when I get my food, I first have to re-encode how did I get here so I can remember this path. And they also do this planning. So how am I going to walk from here? And that this is, we can decode like that. So I think these are both very nice videos. And to see how important this is, yeah, this will be fun.
Wouldn't you say that you're almost reading the brain
Yeah,
of this animal?
of course. Of course, that's brain reading. And the trick is you have to do brain reading, because else how can you decode sleep? Because of course sleep you can never see the brain. And so they've done it with rodents. It's really easy. They usually use spatial, because spatial makes it always easy if you go to these spatial brain areas to be able to decode. But you could do the same in theory with any content. But it's just always about getting enough information to train the decoder. So one thing is what we wanted to do was find out if these ripples are really that important. So we implanted animals with these electrodes, and we would have 2 conditions. The one critical one is that we would detect the sharp wave ripples when you see the replay, and we would now disrupt the processing in the hippocampus. And that's our sharp wave ripple disruption condition. And our critical control condition is that we still detect the sharp wave ripple, but we play the stimulation at a delay. So it's the same thing. The only difference is am I disrupting the ripple or am I disrupting afterwards? And so the ripple always should be replay. And first off, focus on the little rat who has intact sharp wave ripples. So he learned yesterday that food is here. He comes to my choice point. He thinks a little bit, and he goes to the correct point, even so there's no food there today. If we take the disrupted guy, so he didn't have any sharp wave ripples, didn't have replay. When he comes, he thinks, he tries to make himself really long. I don't know why he doesn't want to decide, but then he goes down the wrong arm. And if we keep watching him, he's a magic animal who manages to do a 4th choice and a 3-choice test, because he goes back to his start location, which is kind of funny. Poor rat. So of course, when we did this, we didn't only have the implanted animals, we also worked with animals in sleep deprivation. So we would always teach them this task, either let them sleep or sleep deprive them, or we would have this sharp wave disruption, control disruption, or just nothing, and do the retest. And what was really nice to show is that we could show that they only remember where food was yesterday if they've slept, not if they were sleep deprived. And we can now mimic this way a sleep deprivation effect by disrupting sharp wave ripples. So showing clearly that it is this memory replay that creates the effect on the sleep effect on memory. Now another task you could use with rodents, very famous task, is the water maze. The water maze was invented by Richard Morris, also known as Morris water maze task. And so this is in Edinburgh, because I used to be in Richard's lab. And you can see the rats, they learn to go to this platform which you can't see, and then we can make it disappear because with magnets it stays now on the bottom, and so we can now test his memory. And I always call this a professional rat, so this is quite a fat old rat actually, and he's really professional. He knows exactly where to go, and he swims perfectly. He's very convinced where the platform was yesterday, or it generally is. He's been trained very well, and so he's like, it has to be here, it has to be here. And then the water's 25 degrees, it's not very stressful. And so we track them and could now track if they spend more time there. That's a good way of testing it. And since these are Atlantis platforms, we have the fancy technique that if they know he's going to actually do a reorient, and now we can release them so that we can make sure that there's less extinction. And now he'll go on there and he'll do his dog shake. So he's really not stressed. I mean, I know with water maze, people always think it's stressful. Number one, it's 25 degrees water. The animals are well habituated. They know that they won't drown. They know there will always be a platform. They know the experimenter will always take care of them. I've seen rats jump back in from the platform because it turns out rats actually always can swim. I mean, you don't have to teach them. They're not like humans. I mean, they like swimming. So we've done this. We taught rats water maze, but we didn't only teach rat. We also taught humans, but no, we didn't put them in a pool. We didn't throw them in and say, find the popper. They actually, the ethics committee would probably not allow that. So that's why they actually learn where a treasure is on an island in a virtual reality. And then they're allowed to sleep, or we keep them awake. And then we retest them, and in rodents we just see where they swim. In humans we ask them to mark where they think the platform was. This was actually partly done at the Donders now with imaging, and we could see a nice cross-species effect where, so in rodents good memory is up, and you see that Aloe versus ego I forgot to explain, but at least we could see that there is a memory benefit of sleep in the allocentric condition. I'll explain in a second what the difference is. And that we could see the same thing, because here memory is downwards. That again, there is only in the allocentric condition in humans a sleep effect, but not in the egocentric. And now what is the difference between allo and egocentric? So the difference is how you train the animals. So in allocentric training, what you actually do is you have different start locations. So they can start anywhere in the pool. And the main thing you learn in allocentric is the location, the space. And then this is hippocampus. So this is something that should benefit from replay and from sleep. In contrast, and so that's what it was. Wait, I'll quickly explain ego. In contrast, egocentric training, you always learn from the same starting position. So you kind of don't learn the place, you just learn it's there. And so this is something you can learn just with a body movement, because it could just be like this. And so that is striatal, so it's a different brain area, and that's why benefit less from sleep. And so we showed that, I showed you before, behavior, that it was this way. What we also did is that we looked at which brain areas the animals use, and we focused on the striatum, the hippocampus, and the medial prefrontal cortex. And we could show that if you sleep, the animals used the whole brain, while the sleep-deprived animals could only use the hippocampus in the allocentric training. In egocentric training, we actually see the same thing. So even so there's no behavioral effect of sleep, there is an effect in the brain and which brain area you're going to use. So you always use the whole brain if you slept, while the sleep-deprived animals, again, were restricted to the brain area that's necessary. So striatum and egocentric and allocentric, it's the hippocampus. Now with humans, we'd used fMRI. We didn't do the gene expression analysis. And then just as a quick picture, so this is roughly the brain area you use in this task. So it's very nice, it's very thing. And what we could see is that it's similar to what we see here in the rodents, where we see that they use the whole brain in both conditions if they've slept. Same thing here. We could see that at after sleep, so after the test, they tend to use the cortical areas more, which we think is systems consolidation. And if we now look at our subgroups, the sleepers and the wakers, we could see that this effect is selectively in the sleepers, and while the wakers don't seem to show that much. So what is sleep doing? Sleep is actually letting you consolidate your memories to your whole brain, and so that you can actually use your whole brain, and you can use more of these long-term brain areas. So this is already my summary slide. So I hope this talk, as I said, you're probably not going to remember a lot of episodic detail, but instead the gist, and the main gist is in a way that you consolidate something from detail to gist form by replaying it and having this cross-brain communication during sleep. And that if you always should imagine the bear jumping on your hippocampus up and down, trying to have you remember an episodic memory and lots of little details. And with that, I would already say thank you, of course, to mainly the people who actually do always the work in the lab. So this is the Memory Dynamics Lab here at the thing where Francesco Pataya and I are sharing. And then, of course, I always want to thank my ratsies and mysies for sleeping and you for staying awake.
Is there a difference between the first sleep and the second and the third after recurrence?
So in nights, you mean after learning? So the first sleep, so it's not 100% clear, because a lot of sleepy memory is, but it seems that it's only the first night. So the first night is the clear one where you have a benefit. If you skip the first night, you won't ever see a benefit. However, if you've had the first night, consequent night can have a benefit. But it depends on learning, because the thing is that most of the tests we use, of course, are very simple. So you usually don't see much of an effect afterwards. So the first night is the clear one. But I think with more difficult things, you would see a long-term effect more. But it's still the first night. If you sleep deprived the first night, it's hard to ever catch up.
And for long-term memory,
Yeah.
is it needed to have more sleeps?
So there we come into the biggest problem with sleep research. We don't know these things because it's impossible to investigate. If I sleep deprive an animal for more than, let's say, 5 days, I mean, I've never tried. My max has been 6, 8 hours with an animal. Because if I sleep deprive him for a week, he's going to die because he's sleep deprived. I can't really ask him about his memory. And so it's kind of the problem we have right now, that a lot of what we want to look at, the sleep has so many functions. So if I can't isolate the function I want to look at without killing the animal. And so it's just, we don't know. We believe, yes, but even then the stuff where we look at this replay, the problem is replay becomes so sparse, because what you're actually probably comparing all these different memories, that it's just very difficult to prove it mathematically, because it's just such a sparse event to then show that it's different from chance. And so that is which we're currently failing at. But it's going to be so we believe it, but we just have no way of proving it.
When you look at the whole night, you see that the deep sleep is mainly in the first, or more apparent in the first part. If you would sleep twice a day, but half as short, would you still have as much deep sleep, or would you have more deep sleep?
So usually one would expect, if you're used to it and you're always non-sleep deprived, you should have the same amount. You should just divide it. And then, I mean, if you do classic, you would still have a 6-hour point of sleep, and then the smaller, in like the non-REM or like the smaller nap or something. Then you would still have probably most of your deep sleep in the main portion. But again, it's hard to. So there is this famous polyphasic sleep in humans where they say Da Vinci did it, which is bullshit. Da Vinci never slept that way. But they say that you can sleep every 2 hours or every 4 hours for 20 minutes. And then you never have monophasic sleep. So you only have 20-minute sleep outs. And they say that if you do that, you can survive with 2 hours of sleep instead of 8. The problem is they once tried to do it, so they approached us at the Max Planck Institute because they wanted us to support them, and we would never be able to do a study like that because it's not ethically okay. But since they asked us to do it, we watched them. And only one person finished it, because it turns out the biggest problem of becoming a polyphasic sleeper is having a girlfriend. Yes, they were all male. I don't know why, but they all were male who wanted to do it. But they, at least the one guy who finished it, he could do it, and he said he was fine. And if you look at his sleep, it's really funny because, yes, he actually has just like 5 20-minute portions across the whole day. But if you now zoom in, he has a complete non-REM cycle spread across 5 subcycles, which we found quite funny. But he still never had REM onset because he still would do a little bit of non-REM stage 2 before going into REM. But so in his case, he really had then across the day, like he would have this deep sleep at the beginning of REM. But he stopped after that. So. Good.
Oh, thank you, Lisa.